Hello everyone, welcome to Quantum Guruji. So this is the fifth video in the series of this basis set. And till now we have seen that how to choose a basis set for a specific molecule and how that is going to give you the better results. Now in this video I'll be talking about the different methods and the basis set and how it is going to affect your result and in time, how much time it is going to take. Okay, apart from that, I'll be also talking about the BSSE, that is the basis set superposition error. How does it occur and how to overcome this problem? So, so this now we have having a different methods and a basis set. Okay, so in a x-axis we are having the increasing electronic correlation, and the y-axis we are having the different basis set. Okay, so the basis set start with the minimal basis set split balance, then going to the infinity basis set, and the x-axis it is going to full configuration index. So if you are getting using a infinity basis set and a full configuration index, you will be getting the exact energy of the system, right? But at the same time, it will be taking lots of time of your CPU, as well as accuracy will be increased. So this is just a basic, idea kind of thing. When you are increasing the basis set, the level of theory or the electronic correlation, you'll be getting the better energy of your system, right? So what in this video here, so now we have calculated the energy, right? We got the wave function. Now what is the wave function? Wave function is nothing. It is going to be it is the atomic orbitals, right? This molecular orbitals. Now using that you can find out the specific molecular orbital for the specific molecule. You can find out the other orbitals, atomic orbitals from this thing. Okay, now going to the next part of this video, that is the basis of superposition. Okay, okay. So first thing is, what is basis of superposition? Okay, so we'll understand. Suppose you have a molecule, okay, and you have suppose two molecules. Just assume this is molecule one. Just So just assume you have two molecules. This is molecule one, this is molecule two. Okay. When these molecules are nearby, okay. Now right now they are acting as a monomer, or this is suppose they are the dimer of any molecule. Okay. This is one part of molecule, this is another part of molecule. So when these both of the part of molecule, when you are giving a basis set, what happens? The basis set that you have given for this molecule or this molecule, they will be uh, it will be interact. Okay, how it will suppose whatever basis set you have given for this, it will interfere the basis set of this guy. Okay, and based on that, what will happen? The interaction energy will be overestimated. Okay, suppose you should get some amount of interaction energy, but in this case it will be overestimated and you will be getting more interaction energy, and that's because of this basis set superposition error. Okay, so what happens is that this monomer is still the basis set of another interacting molecule. That's what. So because of this, the lowers the energy of timer in a way that not possible for isolate molecule leading to the overlapping of basis set. And because of this, what happens? The energy, it gets affected, and you are not getting the correct energy of the system. Suppose you are having a molecule A plus B, you are having this AB molecule. So interaction energy of this molecule, you will be getting energy of AB minus energy of A and energy of B. And this way you will be getting the exothermicity or the interaction energy of that molecule, right? If the interaction energy is less than, we call this as stabilizing. Now, if you are getting basis set superposition error because of like interference of two basis set of the monomers, so how to eliminate these basis set? So there are so many ways, but famous, like popularly we use CC correction, that is the CP correction, counterpoise correction, and another is the we choose to use a better or infinite basis set. In both way we can get the eliminate this basis set superposition error. Okay, So in the counterpoise correction, what we do is we reform the entire calculation using mixed basis set, and the error is subtracted from the uncorrelated energy. Okay, using this formula, we'll be finding, like we have taken an example from molecule. It is going to give you the AB. So using this equation, we will find out the BSSE, that the basis of superposition error, and we will subtract this energy from the total energy of the molecule. And another way of using is use infinite basis set. In case of what happens, you are using complete basis set, so you'll be getting energy related to the complete basis set. That is nothing, that is the interaction energy, that overestimation of the energy or the exothermic energy of the molecule. Okay. Now what you do, the total energy of AB molecule. So using this basis set, incompleteness error will be getting from this, and at the infinite basis set, what happens, the basis set superposition error will be 0. Okay, so in that case, the BSSE in this equation will be 0. So this is the AB interaction energy, the interaction energy of this molecule minus the energy of BSIE, that is the basis set incompletence error. So in this way, you can also find out the total energy of your molecule, and that will be the error-free energy. So in this way, you can tackle this problem related to this basis set superposition error. And if you see the Gaussian software, there are various basis set available for different molecules, different elements actually. So you can say this is the basis set, and these are the elements from hydrogen to xenon, from hydrogen to chlorine. So these are the specific basis set, and available for what element it is there. So you can check out the Gaussian manual, whatever you are using. Suppose you are using Gaussian 9, so it will be I think 9 and 16, there are certain difference in, they have included certain more basis set. Now I'll give you a brief review or overview of like what we have done here is. So first, what we are doing, we are deciding a geometry of a molecule. We design a molecule and we keep the geometry of that molecule specific. Now what we do, we calculate the properties of that molecule, and to calculate the properties of molecule, what we give, we take some method we use and do some assumption, and also we select the basis set. Right, we select the basis set and the basis function. After using this, we do a calculation and we get a wave function. Right, this wave function will give you the wave function is what, atomic orbitals, right? So atomic orbitals on linear combination of that atomic orbitals, we will be getting the molecular orbitals. And that's what we use for explaining the properties of molecules, so on. So this is the take home some molecules. What you need to do is you need to find out the appropriate basis set for this molecule. Okay. First, I will tell you, in this molecule you have a cation. Yeah, it has a positive charge, and in the molecule 2 there is a weak interaction. There is an interaction between this OH and this carbonyl group. So there is a hydrogen bonding interaction. Okay, and this is a phenol. So for this molecule, try to find out the basis set. Thank you.